So these are few of the applications of minimum volume ellipsoids, and mostly in path planning. It is not just limited for outlier detection or using classification and discrimination tasks. Even the ellipsoidal surfaces for discrimination, these can be extended for path planning and not just discrimination and classification. Though this lecture is based just on classification and discrimination, but in the upcoming lectures I will extend this approach for path planning. And you can see few of the research papers on support vector path planning that were based on using support vector machines for path planning applications. We just need to formulate proper objective function, and then you can also use this support vector machine for path planning or classification discrimination. It depends on application. So you can refer to these research papers. I will explain them in few weeks. Consider problem least square. The problem is linear in parameters. Your parameters are W, vector W of W0 to Wn transpose, and likewise a feature vector x0 to xn transpose, where x0 equal to 1 and W0 is not equal to 1. W0 is equal to B. This is not 1. W0 is not 1. W0 is equal to B, and x0 equal to 1. This is a mistake. So this is your problem. You need to minimize this function, and this is your prediction W transpose X. Your objective function is to minimize the error between each of the training set, the summation of error over each training set. Now consider this SVM as two-class classification problem, a set of values of A for which y equal to -1 and x represent the set of values of class B for which y equal to +1, and your objective is to minimize this norm. Your norm of W is Euclidean norm of W plus gamma times, which is a parameter, bias parameter or trade-off parameter between these two objectives, gamma times 1 transpose U plus 1 transpose V. So with subject to following constraints, your constraint number 1 is x times W plus B must be greater than or equal to 1 minus U. This is not a scalar, it is a column vector with all components 1, and likewise TW plus B is less than or equal to negative of 1 minus V. With constraints U is greater than or equal to 0 and V is greater than or equal to 0. That is a constraint on each of the components of U and each of the components of V. They must be positive. This is a description of SVM. Now consider quadratic function for your discrimination. The central ideas problem is linear in parameters and can be solved as a feasibility problem via SDP. This is basically an SDP feasibility problem. This was your linear programming, and this is your semi-definite programming. So this is a semi-definite programming. X transpose P times Xi plus Q transpose times Xi plus R is greater than or equal to 1. Your Xi represent each of your training example. For each of your training instance, this equation must satisfy, and like for class A, you can say of positive class, and likewise for positive class, this equation must satisfy, and likewise for negative class, Zi transpose times P times Zi plus Q transpose Zi plus R is less than or equal to -1. The shape of discriminating function can be chosen by setting constraints on P. Like if you put constraint that P is, since we are interested in ellipsoidal surfaces for discrimination, therefore we are putting constraint that P is negative definite, that is separating surface is ellipsoidal. Your constraint on P is negative definite. This will give you an ellipsoidal surface separating the two classes. So this is an example. Consider this is your data set. It is clearly a separable data set and can be separated by an ellipsoid, and this is a separating ellipsoid that you will get after solving this SDP feasibility problem. This is the ellipsoid that you will get. Now consider a non-separable, that is non-separable data set, and your constraint is that each of your training instance from class A must satisfy this condition, and likewise each of your training instance from class B must satisfy this constraint. But since this is non-separable, this data set is non-separable, these two classes cannot be separated, Therefore this is an infeasible SDP. If you solve this SDP, then you will get a result that this is an infeasible problem. So that is, there is no ellipsoidal surface that can separate these two classes. Now I'm introducing minimum volume ellipsoids. How you can incorporate minimum volume ellipsoids for separating the non-separable classes. Okay, I considered this dataset in such a way that after fitting this ellipsoid, this dataset becomes separable. But in general, you have to run the same algorithm for two or three times. Like you run this algorithm one time and still you are getting an infeasible SDP. You again run the same algorithm and then again remove the points, then again likewise. You need to have some visualization over your dataset, like what is your dataset looks like. If you can have an idea of your dataset, then you can easily incorporate minimum volume ellipsoids for determining your outliers. But in general, I'm not guaranteeing that this is always possible through this method, but many times it's very useful. And in just few lectures in machine learning, I will show you how to avoid using clustering algorithms and incorporate minimum volume ellipsoids. And I will also present an algorithm for cluster reduction. So consider a set C and ellipsoid of minimum volume that contains this is a definition of Lowner-John ellipsoid. That is, an ellipsoid of minimum volume that contains a set C is known as Lowner-John ellipsoid of set C. This is just a definition of Lowner-John ellipsoid. This is also known as minimum volume ellipsoid. Now consider a set C of vector x, x1, x2, x3, x4, all your vector of n dimension. Now consider an ellipsoid E, that is set of all x such as norm of ax plus b is less or equal to 1, where a is positive definite. Your Sn++ is set of all positive definite symmetric matrices, and your A is positive definite, that is positive definite symmetric matrix. Now in the upcoming slides I will show you why there is constraint on A to be a positive definite matrix. We will tackle this problem. Now this is another fact: E covers set C if and only if it covers the convex hull of set C. This is very obvious fact. Your ellipsoid E, if it contains set C, it means it will also contain the convex hull of your set C. The problem of finding minimum volume ellipsoid now reduces to minimize the log of determinant of A inverse subject to norm of Ax plus B is less than or equal to 1. Each of your vector in the set C must lie inside this ellipsoid. Therefore, there is a constraint that norm of Ax plus B is less than or equal to 1. And since we are finding the ellipsoid of minimum volume, therefore we are minimizing the log of determinant of A inverse. We can also maximize the log of determinant of A, but we are minimizing log of determinant of A inverse. The objective function and the inequalities were both convex in parameters, and this will be cleared if you watch lectures in information channel. And now note that the variables here are A and B and not the vector x. We already know the vector x, and we need to find A and B, and which are the variables for our ellipsoid. So this is the reason